but there is some sense in which they can be thought as separated problems in the sense that what's an optimal matching? What's a stable matching? What is an optimal matching? And optimality, we don't need to be talking about Pareto. We can just maximize the sum of everybody's utility because we can transfer money. So this is a market where people think about money. We can translate every utility in terms of money. So what's an optimal matching? The one that maximizes the total surplus of the whole society. These are the matchings that are going to be stable. If you have a stable matching and an optimal and a stable price, every combination of these two guys is going to be stable too. Okay? So this is like a Cartesian product of two sets, the set of optimal matchings and a certain set of prices or transfer. Yeah? And again, we have mechanisms that can take you to these outcomes, and in particular, there are mechanisms that yield the Bayer optimal competitive equilibrium. So the Bayer optimal is the lowest possible prices, stable lowest price, or to the seller optimal, which is the highest stable prices that are not manipulable by the buyers and sellers. So these are the two type of markets, matching models that we can analyze. In this paper, what we do is somehow we extend the assignment model. So Marilda worked a couple of years ago, in 92 and 99, on some generalization of the assignment game. Remember, the assignment game is what I call a situation in which we not only care about the matching, but also about the prices. So there are transfers. So you can generalize these models to possibly more realistic models in many environments in which a buyer can buy several objects. He might be interested not only in just one object, but in several. And sellers can offer several objects. Okay, this is what was introduced first in 92 by Marilda in the model that she called multiple partners assignment game. Okay, so these are matching models, two-sided. Still, it's clear who is the seller. It's clear who is the buyer. So it's not like in a competitive environment that we often analyze, in which we have initial endowments, and then depending on the price, I can become a seller, I can become a buyer. In here, who is a buyer and who is a seller is very clear. But people can be very, very heterogeneous in the way they look at objects. So each seller is going to be allowed to have several identical objects, and each buyer may want to buy objects from different sellers. And in this particular market, a competitive equilibrium can be defined easily. So just a vector of prices, so that given the prices, everybody is somehow happy. So buyers can go to the market, they look at the prices. If I can buy 3 objects, I can choose. I can actually buy a set of 3 objects among my most preferred bundle of objects. So this is competitive equilibrium in some sense. Okay. And of course, you don't sell even though your prices are at the lowest possible level. Okay, so this is a competitive equilibrium. Now, once we have defined a competitive equilibrium of stable allocation, which is similar in this case, we can say, look, we have this very nice idea that for each market we can identify one particular competitive equilibrium. So let's call it a rule. So you give me the market, I have this rule. I tell you which is the competitive equilibrium that is associated to the market. Okay, so this is a rule. We call it a competitive equilibrium rule. Okay, so this is just a function that tells me you give me the market, I give you the allocation that you are supposed to be taking. Okay, but of course this is a problem because if we are talking about a rule, and if I'm the designer of this rule and I want to implement this particular stable, nice allocation, I need information. You don't like the presentation, you can tell me, and you. This is the first time she hears this presentation from me, so she's nervous for sure. So again, so we have this rule, right? Now the problem is that if I want to implement the rule, I had to ask you, hey, what's your evaluation of the object? So what's your, as a seller or as a buyer, right? But you might be telling me the truth or not. Okay? So this rule somehow induces a strategic game in which who are the players? The sellers, the buyers, everybody's a player because they can be telling the truth or not. The preferences derive from the true valuation, but the strategy are anything. They can say anything about the valuation. So this is a game now. But now the outcome is defined by the rule that I'm supposed to implement, which is this competitive equilibrium rule. So our objective in this paper is to study agents' behavior when we propose them this rule. For this particular, again, many-to-many market. So what do we know about this market? We know things, okay? So we are, of course, not the first to analyze strategic behavior in this competitive equilibrium rule. Now, there are papers, actually relatively old papers, that discuss the incentives to manipulate these rules in the assignment game. So we concentrate in one-to-one, so we don't generalize one-to-one. So what do we know? So we have a non-manipulability theorem, which is nice. We tell me, look, if I propose you the best allocation, the best stable allocation, or the best competitive equilibrium for the buyers, and you are a buyer, you have no incentive not to tell me the truth. I'm already proposing the best for you in terms of stability. So if I ask you your evaluation and you're a buyer, you will tell me the truth. You have incentives to tell me the truth. Okay? So this is what is called the non-manipulability theorem. That works for the assignment game. It also works for the marriage market, by the way. Okay? But there's another less negative theorem that tells me, yeah, but this nice behavior by people does not generate that easily. You know, for any competitive mechanism, or we can always find some markets in which some people is going to lie to me, not to tell me the truth. So we cannot identify rules such that everybody is going to be sincere when I ask them about their preferences. Okay, this is what is called the impossibility theorem. It is impossible to find such a rule. Okay. Now, this there was this literature, and this has given rise on how to do. We call them false theorem because everybody believes they are true, but nobody has proven them before. Okay, so this is a little bit similar to the false theorems in game theory that, you know, many people believe them for some time until somebody much later proves them. This is also a little bit of the same story, and so these are these two false theorems for the assignment games. Again, for the one-to-one model. So imagine you get a market with more than one vector of equilibrium prices. If there is only one vector of equilibrium prices, life is nice and everybody has incentives to tell me the truth. But imagine we have a market with more than one equilibrium prices, which is most often the case. Now, if the buyer optimal competitive equilibrium rule is used, so if I propose you the buyer optimal competitive equilibrium rule, then we can find a seller who has incentives to lie to me. And this is true for every market in which there is at least two vector of equilibrium prices. So this was the first small false manipulative theorem. This is true for every set of sellers and for always. Okay. There is another false impossibility theorem that say, look, look at a market with more than one vector of equilibrium price. There is no way in which I will propose a rule such that nobody has incentives to lie. Not only the buyer's optimal or the seller's optimal, actually no rule, no competitive equilibrium rule has this nice characteristic that nobody will have incentives to lie to me. Okay. So these are two like negative results, let's say. Okay. So what do we do here? So first of all, we formally prove these two theorems, but we prove them in a more general environment. First of all, we prove them in many-to-many, so we don't restrict ourselves to assignment game, but we restrict ourselves to many-to-many. And we do this proof. Actually, we find this as corollaries of more general theorem that we call general manipulability theorem, that actually we have these two false theorems as corollaries. This is for the negative part. For the positive part, we extend the non-manipulability theorem. Remember, the non-manipulability theorem tells me, look, if I only have to ask the sellers, and I propose the seller's optimal, then the sellers will not have incentives to lie to me. Okay? Imagine, but for some reason, I know the preferences for the buyer, for example, and then I only need to buy this to ask the sellers. Then they don't have incentives to lie to me. So we extend this result to markets in which buyers can actually buy more than one object, so many-to-one markets. And the reverse. So we can extend also the theorem that the sellers, I don't know whether I'm talking the other way around, so the buyer optimal equilibrium, competitive equilibrium, is actually also not manipulable by the buyers when we are in a one-to-many matching model, that is models in which buyers only buy one, although sellers may have several units of the good. However, this theorem, we are not lucky enough, or this is the way it is. Actually, this does not extend to many-to-many. So we have examples of many-to-many markets in which both buyers and sellers have incentives to manipulate any rule, actually. Okay. So this is the presentation. So you understood this. You can sleep now. I'm going to, Marilda is a mathematician, so she likes formal and complicated things. So I will go a little bit through complicated things. It's not my fault. It's her fault. Okay, you blame her. But you understood the other things. What I'm going to do is try to put a little bit of mathematics into it. I will try to be brief. Okay. So these are our market. Okay. So what's a market for us? So this is a set of buyers and sellers. So the buyers are P, the sellers are Q. And so we have these N sellers. And each seller owns a certain number. So we call this T key. Don't pay much attention to the notation. Okay. So each seller has a certain number of identical objects. Okay. The objects will be called as the buyers QK. So when you see QK, this might refer to a seller or to an object that is being sold by this seller. It's the same notation. Okay. Now, we also have a set of buyers, M, and each buyer has a certain quota in the sense that this guy can buy up to 3 or to 5 objects. He's interested in buying up to. Okay, he can buy less, but no more than R. Okay, it doesn't want more than one item from a certain seller. So each seller is selling a different type of things. One selling cars, or selling houses, or tomato, or whatever. Okay. Now, if a buyer, let's say buyer PJ, purchases an object from QK at a certain price, rho K, so this is the price. So the price, by the way, should be higher or equal than SK. This SK is the reservation price for the seller. So if the seller is getting less than SK, it doesn't sell, because this is how much he values the object. Okay. So prices, of course, should be higher or equal than this minimum price. Now, the payoff are easy. If I'm buyer J, I'm buying object K at the price rho K, then alpha JK represents how much is this object K worth for me. Okay, so this is my evaluation as buyer J, as buyer PJ of object QK. Okay, so I have a number associated for each possible object. And of course, different buyers can have a very, very different valuation. So it's not like every buyer has allocates the same worth to an object K. We can be very, very heterogeneous. Now the payoff for the seller is even easier. So this is just the price minus the minimum worth of the object for him. Okay, so this is the surplus the seller gets. This is the surplus that the buyer gets if this relationship happens, okay, at the price rho K. Okay, so we also assume that instead of not buying, we buy object 0, or instead of not selling, we can say you sell to the buyer 0. Okay, but this is just for simplicity. Okay. Again, this is an extension of a very well-known and very well-worked type of model assignment, again, of which I already talked to you a little bit about it. This is the one-to-one with money, with all these nice properties I told you. Okay. Now, what's a matching? So a matching can be represented different ways. You can represent a matching through a function that assigns sellers to buyers, for example. In this paper, just because it's more convenient for us, we represent matching through a matrix. So a matrix of zeros and ones. So there is a 1 between buyer 1 and seller 1, means that these guys are transacting. If it is a 0, they're not transacting. Okay, but whether it's a matrix of a function doesn't matter. It's just a way to represent whether the relationship between the partnership actually happens or if it doesn't happen. Now, to be feasible, so for this to make sense, means that each seller is selling of his object, possibly to this weird guy zero that we call this buyer that buys whatever. Okay, each buyer is buying as many objects as he needs. Again, possibly can buy zero objects, and that the price and the relationships are profitable. That is, the value of a relationship, which is this alpha, which is the value of buyer J for object K, should be larger or equal than the value that the seller allocates to this object. Otherwise, the partnership wouldn't make sense. Okay, this is what we call feasible, and it is optimal. Don't look at the formula. It's optimal. It's the best we can do. And the total. So you look at the total payoffs of everybody in this economy after the matching. This is the best you can do. Okay, and if it is the best you can do, we call this matching optimal. This is the best. Okay. Again, we can define it. Remember that in our economy, it's not enough that we identify the matching, who is going to be in partnership, who is going to be buying from whom. We also need to identify the prices in this relationship. Okay, so the prices is this vector rho, that all should be larger or equal again than the minimum prices. So this is what we're looking for, an allocation. What's an allocation? You should tell me what's the matrix, so who is buying from whom, and what are the prices at which transactions happen. Okay. And okay, so let me try to escape a little bit of notation. So what's a competitive equilibrium? Competitive equilibrium, again, is a vector of prices, and it's an allocation such that everybody is happy. And what does it mean happy? That means that given these prices, so these are the prices, one price per object. You are a buyer, you go to this economy, you see these 10 prices, you want to buy at most 3 objects, you go there, you say, okay, given these 10 prices, my best bundle of objects is object 1, 4, and 5, or maybe indifferent between object 1, 4, and 5 and object 2, 4, and 5. Well, I should be able to buy one of these most preferred bundles for me. Okay, I can maximize my utility given the prices. So what the guy buys should be in the demand set of this buyer. And if one object is not sold, it is not sold because even though the seller keeps lowering the price, it still didn't sell it. So prices should be equal to the minimum reservation price for the seller if there is an object that has not been sold. Okay, so we cannot have equilibrium that are artificially high for no reason. Okay. So this is a competitive equilibrium. So what do we know about this market? So these are results from previous work by Marilda in a couple of papers. So if the equilibrium outcome is competitive, then the matching is optimal. So this is a nice characteristic. So the market takes us to a matching which is actually be very good. It's going to be optimal. He also tells us that the same structure that I showed you before, I gave you before for the assignment game, so we can have the optimal matchings and we have the prices, and it's actually like a Cartesian product, so we can mix any optimal matching with any equilibrium prices, and this is going to be stable. This also happens for the many-to-many markets. And also in these markets, there is a competitive equilibrium that we can call it the best for the buyers, which is the P optimal. Remember, P is the buyers. And there is another stable allocation, which is the best for the sellers, that we call it Q optimal. So they have the same nice structure in which you have the best for one side, which happens to be the worst for the other side, and vice versa. Okay, so let's go to the manipulation. Again, we have all the results are very nice, but to be able to implement any of these things, you need information about buyer's valuation, seller's valuation. So otherwise, how do you get there, right? So let's look at it as a mechanism or as a rule. Okay, let's make a game out of it. So let's fix the set of players because we know them. So we know the set of buyers, we know the set of sellers. We don't need them to tell us that they are buyers or sellers. We know that. And suppose also that we know the quota, so we know how many objects each seller owns, and we also know how many objects each buyer is interested in buying, possibly. Okay. And then this is like a market. This is our market. So once we fix all the other, A market is different if for the valuations change, and for the buyer, this is alpha, this set that tells me how much each buyer is willing to pay for an object. This is the matrix alpha. And S, which is the vector that tells me how much each seller values the objects he owns. Okay. Now, what's a rule? Imagine again, I'm the designer. Now you tell me alpha, you tell me S, and I will propose a price vector and a matrix to you. So I like the market maker. Okay, you tell me your valuation, and I will tell you the prices at which you should be trading and who is going to be trading with whom. Okay, this is a rule. Now, of course, this is, you may be telling me the truth or not. So this is a game. This is a strategic game. Now, in this game, we have the players, right? This is P and Q. So each one of the participants is a player. This is the profile of true valuation. So I, as a market designer, I don't know that, but each one of you has actually a valuation for the buyer, for the objects, and both as a buyer and as a seller. Sorry. Now, the strategy that if you are a buyer, you can cheat me, but you can tell me any possible vector of valuation for the objects, and this is your choice. So you can tell me the true vector of valuation. You can tell me something else. So this is your strategy space. If you are a seller, you can tell me that maybe the object is worth to you SK, but you can tell me something else. Okay, higher or lower, whatever is best for you. And now the outcome, what I will do is I would be like naive. You tell me whatever you want to tell me, and I will think these are the true valuations, and then I will propose you the rule that gives to this competitive equilibrium. Okay? But of course, your preferences will be based on your true valuation, not on the valuation you are going to give me. Okay? You can lie to me, but you are who you are. Okay? Okay, this is the game. Okay, so you will say that this rule is manipulable if some of you has an incentive not to tell me the truth. If it is not manipulable, that means that you don't have any incentive not to tell me the truth. Okay. Okay. So what do we know? Remember, what do we know in the assignment game, and how we're going to extend it to other markets? So the non-manipulability theorem, that again is 82, 85, tells me, look, in the assignment game, so if we have a one-to-one matching model, and I, as a mechanism designer, propose you the buyer optimal competitive equilibrium. So the competitive equilibrium which is the best for the buyers. Then now, if you are a buyer, you don't have an incentive not to tell me the truth. So you will be telling me the truth. This is the non-manipulability theorem. So buyers don't have an incentive to manipulate their true characteristics if I offer them the best stable allocation for them. And the reverse for the sellers. Instead of offering the buyer's optimal, I will be offering the seller's optimal stable allocation. Then no seller will have an incentive to misrepresent their true valuation for the object. Okay, so this, in some sense, the rule is nice because it's not manipulable, at least for one side of the market. Okay, this is what we know. Now, can we generalize this to many matching models? The answer is no. So even if we propose the seller's optimal in many market models, still the sellers might have an incentive to misrepresent their preferences. And if I would, again, offer the buyer's optimal rule, still the buyers may have an incentive to manipulate the buyer's optimal. I will not go through examples, okay? But the idea is the following. What happens if you are a seller? So imagine, again, I offer the seller's optimal competitive equilibrium. Now you are a seller and you are offering two objects because you have two objects. Actually, it's a little bit similar as when you are a monopoly. So imagine you are a monopoly and you have two objects, and maybe at equilibrium you can sell the two objects, but maybe one of the two guys who is buying from you actually has a valuation which is very large. So maybe I'd rather sell one object to this guy at a very high price than selling two objects to the two guys at a much lower price. But the very same effect happen in these matching models. Okay, you can manipulate. You are selling several objects to increase your reported reservation value to end up selling not two, maybe, but one, or not two, three, but maybe two. Okay, but this is very much the same, in the same spirit as a monopoly can discriminate, and maybe you don't want to sell to anybody, to all of them. You may sell to a restricted set, but at a much higher price. However, you can only do this. You own more than one object. You only own one object. You cannot do this trick because you try to sell too high, then you don't sell. And this is what this proposition say. No seller can manipulate the seller optimal competitive equilibrium rule through a deviation in which he sells all its objects. So you would only do this to sell less at a higher price. What's an implication? Actually, the easiest implication is the corollary of this theorem. I forget about the theorem by now. The implication is that the seller optimal competitive equilibrium rule for many to one buyer-seller models, so for models in which buyers may want to buy several objects, but each seller only owns one object, is a strategy proof that this is non-manipulable by the sellers. Okay, so it's negative. The result is negative for many to many, but at least it extends to many to one. And we can do the same trick for the other side. For the other side, happens to be a little bit more complicated to explain. So we don't have, at least I don't have like the monopoly story to tell you why a buyer is interested. But let me tell you, a buyer might be interested in manipulating because he can manipulate a price of an object, let's say object 3, and through this manipulation at equilibrium, it happens that the price of object 1 decreases. So you can manipulate the whole system of equilibrium prices. So you can manipulate some prices and end up decreasing the price of other objects. So again, this suggests the same type of result as before, although again the argument is different. Any buyer who is interested in buying only one object cannot manipulate this mechanism. It's only if you are interested in several objects that you can manipulate some objects, the prices of some objects through your offers to other objects in the economy. Okay? So this is and actually, this has a nice interpretation also in terms of auctions. Matching has been fruitful in terms of proposing mechanism and obtaining results in auctions. And this is similar here. What this theorem or this result says is that, in the buyer optimal competitive equilibrium, the price of the object that the buyer obtains does not depend on its valuation. Forget about you don't remember notation anymore, I know that, okay? What this says is, look, if I offer if it is a market in which you are a buyer, you only want to buy one object. And I compute, which is the optimal equilibrium for the buyer side. Now, the price that you are going to pay for that object does not depend on your report. It's independent of your report. So you cannot manipulate it, because whatever you say, this is going to be the price. Okay? And so the same as in Vickrey auctions, you have analyzed auctions. In the second price auction, this is like a second price auction. If what you pay does not depend on your report, corollary, the buyer optimal competitive equilibrium rule for one-to-many buyer-seller models is a strategy proof. So it's not manipulable by the sellers, by the buyers, sorry. So this is the one-to-many means that buyers only can only buy one object. Sellers can sell several objects. Okay. So this is about non-manipulability results. So in the 5 minutes that I have left, let me tell you about manipulability. Okay. What do we know? What we have is actually we have some examples of markets in which the optimal competitive equilibrium mechanism is manipulable by one side or by the other. Okay. What we're going to do here is to prove that this negative result actually is quite general. Not that we want it again. It's just this life. Okay. So this is our general manipulability theorem. Let me just try to read it for you. So imagine that we have a market, that the real market is a market where there is at least two competitive equilibrium. Okay. So if there is only one, nothing can happen. So imagine that we are in a market, as most markets, where there is the set of equilibria is not just a singleton, there are several competitive equilibria. Okay. Now and pick one guy, one seller or one buyer. So imagine it's a buyer. Then one buyer that is obtaining less than what he obtains in the buyer's optimal competitive equilibrium. Any buyer. Okay, so any buyer who gets less than what he gets in the competitive equilibrium, which is optimal for the buyer. Now, this guy has an incentive not to tell me the truth. So if I apply this rule, any rule that I apply, such that it doesn't get as much as in the most preferred stable outcome, this guy has an incentive to lie to me. This is quite general in the sense that it allows us to have this two-fold theorem. This is true, by the way, for many-to-many matching model. So not only to one-to-one, but for many-to-many. So this, as corollaries, this is the first fold manipulative theorem. So you take the buyer optimal competitive equilibrium, and there is more than one rule, then it is manipulable by the sellers. You take the seller's optimal, then it is manipulable by the buyer. This is a corollary. Again, this is a corollary extended to the many-to-many. The other corollary is still, again, trivial. You have any market with at least two competitive equilibria, then it is manipulable by somebody, actually by everybody who doesn't get the best they can obtain. Okay? So, okay, I think I can stop here. For the assignment game, you can have more if and only if properties, but I think this is, this is less interesting. So, but again, what we do here is we extend to some degree the idea that the buyer optimal is not manipulable by the buyer and the seller optimal is not manipulable by the seller, but we can only extend it to many-to-one or to one-to-many. So as long as some people have several objects to sell or several objects to buy, this guy will have an incentive, or might have an incentive to manipulate. On the other hand, the general manipulability theorem, which is like a negative result, actually extends very, very generally to many-to-many, to any market with many-to-many. And in fact, you can show that anyone who is not getting his or her best has an incentive to manipulate, always. Okay, and I will stop here.
So we have time for a couple of questions. Salvador.
Are you going to read it? I'm happy you like it.
Well, my question should be obvious to you, since you heard me. For those cases where you have this partial strategy proofness at an individual level, do you have a feeling whether you will also be able to show some form of group strategy proofness?
Once we say that it should be obvious, I understood the question. I don't know. We didn't check. But maybe we can check your properties, the properties you propose in your talk.
Well, if you delay the check-in for a while, I'll check it for you.
Okay, that's a deal.
Very nice. Is there any other questions? No? Thanks a lot, David.
Thank you.
Thank you very much again. So let's pass for the next session very quickly.
For those of you who do not know me, I'm Maurice Bulgarian from the University of Brasilia, and it's a pleasure and a great honor to be back to EPGE and to host this final closing session. For that, I would like to do something slightly different. I would like to invite a few people to join us here, because this is a more personal and a session from the heart. We're going to celebrate one more time Marilda's birthday. So I would like to start asking Professor Aloysio Araújo to come here. Please sit here. And then Professor David Perez Castrillo. Professor Nash, please come here, join us. And then would like Marilda to be here. So, as you can see, we have all Brazilians here, either born here or earning this because of prizes or because of the contributions that has given to us. And I would like to start asking Professor Aloysio to say a few words to celebrate. Let me remind you that this is a satellite event from the workshop that just finished in São Paulo, and we had a 1-week workshop to celebrate Marilda's birthday, and in addition to the celebration part, we would like to thank Marilda because we could only get such wonderful group of people coming to Brazil thanks to her effort and to her contribution to economic theory and to matching theory, and that's why we are all here. Professor Aloysio, please.
Thank you very much. Again, Getúlio Vargas Foundation has been very proud to this satellite meeting and to take advantage of just great minds that have been here to commemorate Marilda, and then to be part of this event in honor of her. I'm very happy here that I see many young faces here, our graduate students and undergraduate students have the opportunity to take advantage of that, to both absorb and then to honor a person that is an example for us of dedication, working under very difficult conditions, very little resource, both intellectual and material, during all this year in consistent way, and achieving so many scientific results. And for us here in this country, that this country here had its first university in the middle of the, more precisely 1930 only, is less than 100 years, the first university, so it's a country that really come from a very low scientific background, and then education has been very low, and then to have examples of people that dedicated themselves to form new generations and to is very particularly important for us. And I say a few words that also from in Rio is a great opportunity. I mentioned that over lunch. It's not the same group of people that have somebody like John Nash that had been in São Paulo already, but not to Rio. And then for us, I tell the same story that I was in IMPA, and then my friend in mathematics didn't believe that was is the same person, Aloysio, John Nash, that the same mathematician, all know all this beautiful result that won on the prize, Nobel Prize in economics. Cannot be. You are wrong, Aloysio. Cannot be the same person. All this beautiful embedding theorem, hard implicit function theorem, all this geometry, contributes to geometry, differential equation, and then, so I had to prepare a talk. They asked me, Aloysio, you have them to prepare to tell us exactly what it is. So I made the resume very short in the mathematics and the economics, game theory, and how the unifying characteristic of his concept was so bright. The ideas had appeared here and there, but had such a powerful unifying concept of equilibrium and existence. And then I learned that even some of the existence proof were his also. Not only the basic Kakutani, but also these other more simple. So it's amazing. So we for us, again, in a country like us, that education has been so lagging behind, and then to thank you very much for John Nash to come. Thank you very much, Marilda, for everything that you've done to us, and the organizer of the event that made us possible, and this university here, Getúlio Vargas Foundation, that made this satellite contribution, Humberto, Rubens, and Carlos Ivan. Thank you very much.
Thank you, Aloysio. Now, Professor Perez Castrillo is going to tell us a little bit about the contributions of Marilda.
Okay, so I will read, because this, so I prepared a little bit about Marilda's contributions to economics. So, okay. So when Humberto and Danilo were so kind to invite me to say a few words on the works of Marilda in this closing session, I was very happy, of course, to have the opportunity of participating in this celebration and briefly report on her contributions, which also gave me an excuse to go back to some of her papers. So let me first thank the organizers of the conferences, in particular Humberto and Danilo, for the honor that they made me with this invitation. Actually, we were discussing with Salvador and with Inés before the Sao Paulo conference that this is a year of celebration, of 70 celebration, where a few weeks ago we were celebrating in Amsterdam the 70th anniversary of the game theory, the Games and Economic Behavior book by von Neyman and Augustine, and now we are here a few weeks later celebrating the 70th anniversary of Marilda. I think this is a nice matching. So although Marilda is now very, very famous because of her work on matching models, matching theory is not the first area in which she contributed, as some of you know. During her PhD dissertation at IMPA, from 78 to 81, she worked on the solution to growth models under the supervision of Jan Schechtman. In particular, she characterized the optimal dynamic behavior of consumers in several environments, including economies where the production function is random and not necessarily concave. So she analyzed big mathematical problems related to growth theory. Marilda wanted to continue working on economic growth. So in January '83, she went to the University of California, Berkeley, to learn from the famous mathematician David Gale, who had been the supervisor of Jack Schechtman. So that is David Gale is I understand, the academic grandfather of Marilda. And as reported by herself in the article My Encounters with David Gale, who was published in Games and Economic Behavior, and a special issue to honor David's memory, the first meeting between the two mathematicians ended with a sentence that has been crucial in shaping Marilda's research career. David Gale stated, "I am not interested in this area." After the disappointment, Marilda decided to use her visit to learn from David Gale on the topic, or one of the topics he was interested in at that time. And this is why she started reading the pioneer work on matching theory, the famous paper by David Gale and Joyce Shapley in 1962 on the college admission problem, and the short book by Donald Knuth published in 1976 on stable matchings, as well as the more recent papers at the time by Lester Dubins and David Freeman, published in 1981 on the non-manipulability of the Gale-Shapley algorithm. It's a little bit similar to what we saw today, to allocate the students to colleges, and also the paper by David Gale and Gabriel Demange that was published a little bit later in 1985, where the lattice properties of the set of stable allocations and the non-manipulability result were extended to the assignment game. That is to, as we saw before, matching models with models. Model assignment game, a model that was introduced back in '72 by Joyce Shapley and Martin Subik. Now, Marilda visited David Gale in 1983 and '84. And she wrote with David Gale 4 very influential papers for the matching theory. Two of them were also co-authored with Gabriel Demange. Three of these papers, published in mathematical journals, concern the marriage and the college admission models, and they prove properties that have become classic properties nowadays. First, they prove the famous blocking lemma, that for non-stable and individually rational matching identifies a particular blocking pair that is preferred by some agents on one side of the market to their optimal stable matching. The blocking lemma has been an instrumental result to prove key properties of stable matchings in general. They also prove, among other results, that the set of unmatched people is the same for all stable matchings. That the addition of, say, more positions in colleges cannot be bad for the applicants and cannot be good for the colleges. They also prove that the applicant optimal stable matching is in fact Pareto optimal for the applicants among all possible stable matchings, and also that women have an incentive to manipulate the men optimal stable matching, or vice versa. In the fourth paper of this series, that was published in the Journal of Political Economy, the three authors, David, Marilda, and Gabriel, analyzed dynamic multi-item auctions for the assignment game that achieve, either in an exact or in an approximate way, the best equilibrium from the bidder's point of view. In the workshop in Sao Paulo that just finished yesterday, we still listen to new results on auctions that are similar to the one that the three of them proposed in '86. 2 months after she finished her visit to David Gale, that is around March '85, Marilda started the first of the many visits that she made during the following 13 years to the Department of Economics at the University of Pittsburgh. And she initiated a very fruitful collaboration with Al Roth. With Al, Marilda wrote 2 papers, one on the college admission model and the other on the assignment model. Concerning the first of the models, in their '89 econometrica paper, they showed the surprising result that in a model where preferences are strict, if we consider 2 different stable matchings, in a model where, then each college prefers every student who is assigned to it in one of the matchings to every student who is assigned to it in the second matching, but not in the first. On the other hand, their '88 paper published in the Journal of Economic Theory analyzed the structure of matching outcomes for the assignment games that are stable, but they are not optimal for one side of the market, extending and generalizing previous result by Sharon Rochfold. If her collaboration with David Gale introduced Marilda to the matching models, her collaboration with Al Roth has been instrumental not only for the subsequent research that Marilda has been developing, but also for the advance of the game theory of matching. Indeed, the book Two-Sided Matching, a study of game theoretic modeling and analysis that they published in '90 in Cambridge University Press, has been extremely influential. And he has made the theory accessible to thousands of researchers and students. The elegance and rigor of the book make it a very pleasant and fruitful reader, as it was recognized by the Lanchester Prize in 1990, awarded by the Operation Research Society of America. These qualities also make the book appealing not only for mathematicians and economists, but also to many other researchers in social science and to public regulators. This was true in 1990, and surprisingly, is still true today. It is interesting to note, or a curiosity to note, that in his praise of the book, Uriel Rothblum wrote, "Every once in a long while, a book comes along with the potential to change the way in which an entire field of study is viewed. This book has that potential." It is clear, I think, to all of us that this potential, this prophecy, has really been fulfilled. After her collaboration with David Gale, Gabriel Demange, and Al Roth, Marilda's contributions to matching theory have been numerous. She has extended the existing models in various dimensions. She has provided new properties. She has proposed simple mechanisms to implement the stable allocations in several models. And she has even given simple, short, and elegant proof of classic results. I will certainly not review all the results that emerged from Marilda's paper. However, I will take some time to briefly illustrate some of her contributions. I will do this by topic and not by publication date. First, Marilda has extensively worked on the college admission problem, that is, models in which there is no transfers of money. In one of her papers, for instance, she provided a very short and simple proof of the existence of stable matchings in the marriage market. The proof of these 96 papers that was published in Games and Economic Behavior is non-constructive and is quite different from the original proof of Gale and Shapley, which relies on the famous algorithm. And actually, she gave rise to other extensions in models in which this algorithm cannot be applied. She also developed several analyses on the differences between various possible definitions of stability in this type of problems. In 1999, in a paper included in the issue that Mathematical Social Sciences dedicated to David Gale on his 75th birthday, she discussed the differences between the core and the set of pairwise stable matchings, two sets that she proved can be non-empty but still disjoint. She also proved that pairwise stable matchings always exist in college admission models if preferences are substitutable. Very recently, she has come back to discussing the right definition of stability in the marriage market, including additional possible blockings by the Grand Coalition. Also, for the college admission model, Marilda has analyzed agents' non-cooperative behavior in several mechanisms. The typical type of games that she has analyzed has the following sequential structure. In the first period, first players from one side of the market, let's say men or firms, choose a set of players from the other side. In the second period, the players from the other side, so women or workers, select partners out of those who have chosen them in the first place. And Marilda has shown that the outcomes of this type of sequential mechanism are often nice in the sense that they are stable. And the nice properties of the equilibria hold for the marriage, that is for one-to-one model, as well for the many-to-many model, although sometimes to a lesser extent. Finally, she has analyzed agents' behavior when stable rules are applied. That is what happens if naive designer organizes an institution that leads to a good, stable outcome if the agents are honest about their preferences. Do they really have an incentive to report the true preferences? We saw just a while ago what's happening in some of these cases. The college admission problem has become very popular because of all its applications and in such important problems as the allocation of physicians to hospitals, students to schools, and kidneys to patients. And many real markets have greatly benefited from the results and proposals that researchers in the area, in particular Marilda, has made. All these situations involve ordinal preferences, in the sense that what matters is the ranking of the agent's preferences, but they are not monetary transfers that can compensate agents from one side or the other. The second group of Marilda's contribution refers to the matching problems where monetary transfers are feasible and they are a crucial part of the deals. The assignment game constitutes the simplest class of problems as it concerns situations where agents from each side of the market can deal at most with one agent from the other side. On this assignment game, in addition to her initial contribution with Gabriel Demans, David Gale, and Al Roth, Marilda has worked on the characteristics of the core, in particular when there is only one optimal matching and then the set of stable payoffs constitute a complete lattice. She also proposed in a joint paper that we started while she was visiting the Universitat Autónoma de Barcelona in '96, a simple selling and buying procedure that in equilibrium lead to the maximum equilibrium price vector together with an optimal matching. That is, this paper contributes to the message that matching models are not only nice because they are useful and they have very elegant and beautiful properties concerning stability and competitive equilibria, they are also nice because we can design reasonable non-cooperative games whose equilibrium outcome lead to stable or competitive allocations. This was my first collaboration with Marilda. It was, of course, nice and stimulating working with a leading expert on a topic about which I only had very limited expertise. I was lucky because Marilda was very generous, and I managed to learn a good deal about matching models by working with her, knowledge that I have later applied to in other papers. Also, on a more personal note, let me just put a small personal note on this. Let me stress that the pleasure of working with her was accompanied by other perks. Our first paper, which was published in the Journal of Economic Theory in 2002, received the prestigious prize Aralambos Simeonis awarded, and I quote, to the best paper by Brazilian economists. So my understanding is that since that date, I am Brazilian economist, so I am very happy to be back home. Already in '92, in a contribution to the book Dynamic and Equilibrium, essays in honor of David Gale, Marilda proposed an extension to the assignment game to what she named multiple partners assignment game, and I just introduced in my lecture. It's a model where each participant can form more than one partnership. In a series of papers, she has proven that many of the properties of the assignment game, so the one-to-one model, also hold for the multiple partners assignment game. In particular, the set of stable payoff is non-empty. They form a complete lattice with a unique optimal stable payoff for each side of the market. She also compared, for this class of game, the concept of cooperative and competitive equilibria. Additionally, she has proposed mechanisms that lead to competitive equilibrium payoff, and she has analyzed other variants of markets where each agent can form several partnerships. Since I already talked a little bit about these models, I will not extend more on this. Finally, let me mention that Marilda has also contributed to models outside the classic marriage or an assignment model. She has studied the stable set of mixed economies or hybrid markets in which some firms are flexible in the sense that they can choose salaries, whereas other firms have no flexibility. That is, it is a model where some agents behave as in the assignment game, whereas others behave as in the marriage market. Their preferences are ordinal because they cannot choose salaries, actually. The set of stable matchings is also non-empty in these extensions of the models, and the lattice properties of the core is preserved. Properties concerning the entrance of firms and other properties might not be preserved in these hybrid models. I am sorry to keep the suspense, but I cannot tell you the end of the story about Marilda's contributions to matching theory, and I cannot because it is an ongoing history. In the last talk in this workshop, I had the opportunity to present one of her most recent working papers on the manipulability of competitive equilibrium rules in many-to-many buyer-seller markets. We're also collaborating in other projects to study outcomes of simple mechanisms for the assignment game. In Sao Paulo, we had also the opportunity to present some other of her current research. She presented last Friday a paper on cooperative equilibrium. So I can only say that I look forward to the next celebration, including dancing, I hope, where her friends can gather again and we can continue to report on Marilda's impressive and influential contribution to matching theory. Marilda, happy birthday.
Thank you very much. Since you are Brazilian now, you have to choose a state now. Are you going to be Carioca, Paulista, or maybe Brasilia? That's a difficult
I will choose, but I keep it secret now.
That's the best choice. Now,
I would say maximum a month.
But then for the next ones that are going to come, there'll be another paper there. And now I would like to ask Professor Nash to say something about your memories with Marilda for her birthday.
Recreate what I said a few days ago, and a celebration in Sao Paulo. When they had a party, various people were coming up and giving their memories and connections with Marilda. And this is not a big story, but I happened to meet Marilda for the first time at a place called the Three Village Inn in Stony Brook, in Stony Brook, Long Island, New York. And she actually has a picture from that time that shows her and me at a breakfast table. The thing is, the Three Village Inn was one of the places where visiting speakers could stay, and it was desirable, rather desirable, if you did not have your own car. And that was my situation in those times. And, well, there was a family car, but I didn't take it with me to use it when I would be at Stony Brook. But also, it was when I met her, it was that I saw her at breakfast at this place called the Three Village Inn, which was nice in many ways. It's still there, but it's, as a hotel, there's something more convenient. And there was also the time of William Thompson. William Thompson was here at Sao Paulo recently. He, of course, like me, like all of us, is much older now than when I first met him. He is a little unusual in that he seems like an American, except that his name is Thompson rather than Thompson in his spelling. And he said, I saw him very recently, and he said, well, this is the Scottish spelling rather than the English spelling. But he's really French rather than Scottish or English or American. He lived in France, but his name doesn't show it. But he appreciated the tea, the morning tea, and you can get an English breakfast tea that's not bad. And the Three Village Inn had some variety of cereals that you could choose from in the morning. So I got to meet Marilda like that without really going into any mathematics or theory, any discussion of work. And it's a very memorable experience.
Thank you very much. Then let's end the session. How about another happy birthday? Happy birthday to you. Happy birthday to you. Happy birthday, dear Marilda. Happy birthday to you. Thank you all for coming.
No, I didn't prepare any speech for today. I am very tired, and I survived the organization of the workshop in São Paulo. But he gave me this. Then the only thing I can say is that I am very honored and with the presence of everyone here. And it is the birthday I have that I think the most commemorated birthday, most celebrated birthday. Okay, I have celebrations in everywhere. Here I had 3, no? In São Paulo, many. Okay, thank you very much.
May I ask Professor Rubens Cisne to close the session? There's a microphone there.
I think we had a wonderful day, a wonderful morning, wonderful lunch, wonderful sessions. Just once more, let me say how deeply, deeply happy we are and honored by, as Luisa said, honored by honoring you. Thank you very much, all of you.